All right, looks like there's no question. So I'll begin with the lesson today. I'm going to go ahead and share the screen. And then if I could get a few people to just confirm that they can see. Then, all right, sounds like somebody's, all right, very good. All right, so what we're doing today is we're going on with talking about how to do hypothesis tests for the mean of differences. But before we do that, I did get a student question, which I think would be good to go over. So this will be a good review of the last couple of classes. This is a question from your homework that has multiple parts in it to help guide you to make sure you're considering all the parts that will help you get the question correct. So I'll read here. It says, in a study of accuracy of fast food drive-through orders, one restaurant had 36 orders that were not accurate among 342 orders observed. Use a 0.10 significance level to test the claim that the rate of inaccurate orders is equal to 10%. Does the accuracy rate appear to be acceptable? Identify the symbol to be used for stating the hypotheses. All right, so when stating a hypothesis or a claim about a population, you will use the population parameter symbol. There are two types of hypothesis tests that we've been working on, and one is a test about a proportion, and one is a test about a mean. So I'm looking for a population parameter symbol, either a population proportion, which would be P, or a population mean, which would be mu. So I just need to consider the question we're looking at and determine whether this is a population proportion question or a population mean question. So it had said it gave us a certain number of basic successes out of a total number of sample values so that we can make a percentage and test the claim that something is equal to a percentage. So when you're testing a claim that involves a percentage, that would classify as a proportion. So we would want to use P, the population symbol for population proportion P. Next, we want to identify the correct equality or inequality symbol for the null hypothesis. The null hypothesis always uses the equal sign. So we'll just go ahead and choose the first option here. And then the next question says, identify the correct equality or inequality symbol for the alternative hypothesis. All right, so in order to determine the alternative hypothesis, we need to know what the original claim was. So let's write down the original claim in symbols. The claim was that the population proportion P is equal to 10%. So that's my claim in symbols. The alternative hypothesis, if there's no equality in the claim, then the claim will be the alternative hypothesis. However, if there is equality in the claim, then it falls under the null hypothesis, and therefore the alternate hypothesis must be the complement of the claim. So what is the complement of the claim? Strictly not equal. So we'll choose option D. Next, identify the test statistic. test statistic. Okay, so statistic is a sample measurement. And since we're doing a claim about a proportion, the sample proportion or the sample statistic is the sample proportion p hat. And to make it into a test statistic, we will need to standardize it. So let's find the p hat first, and then we'll standardize it into a score. So back in the problem, the sample information given was 36 orders out of 342. So this is our x and this is our n. The sample proportion, and I like to use green for sample stuff, so I'll switch here. So the sample proportion p hat is found by taking the number of successes divided by the sample size. So we'll take that 36 and that 342 to make our sample proportion. It says round to 2 decimal places, but remember, we're not just asked for the statistic, but we're asked for the test statistic. So I want to change that into a z-score. I want to standardize it. And the formula for standardizing a sample proportion is found here in the formula sheet for, remember the right side is for test statistics, and this would be the correct one when dealing with proportions. So notice it's p hat minus p over the square root of pq over n. All right, so now we just need to fill in all the values. So p hat, 36 out of 342, minus the population proportion. Now, what is the population proportion? Remember that we are always doing a hypothesis test under the assumption that the null hypothesis is true. And the null hypothesis always uses the equal sign and the same value that was mentioned in the claim. So the population proportion will be 0.10. The n is 342, and the p is 0.10. So what does that mean the q must be? For the p is the success rate, and q is the failure rate. So they have to add up to 1, and that means that q would be 0.9. So let's calculate this. You can use a calculator or Excel, which is basically a giant calculator. So we have, let's see, equals. We always start with an equal sign to make a cell do a calculation for us. Then we're going to want to enclose the numerator in parentheses so that the whole top will get divided by what's in the bottom. And I need the 36 divided by 342 minus 0.1. There's my numerator. Let's divide that. Notice that the bottom has a square root over everything. So I'll go ahead and make a square root function in Excel is sqrt. And then I'll put in 0.1 times 0.9 divided by 342. Close that with another parenthesis and enter. So I got 0.324. Let's see, what was rounded to 2 places? 0.32 then? 0.32. The test statistic, 0.32. It's actually a z-score. All right, and let's try that with the question that I was sent here by the student. I'll go ahead and put in all the answers that we did so far. The symbol for stating the hypotheses is P. The null hypothesis uses the equal sign. The alternative hypothesis uses the not equal sign. And the test statistic to 2 decimal places, 0.32. And we can't check them as we go, so I guess we'll have to keep going because this isn't set up to do little pieces at a time. So next we'll do the p-value for the hypothesis test. Let's write this here. Why do I keep putting that 0 afterwards? Should be 0.32. All right, the next part, the p-value for this hypothesis test is. Now, the p-value is the area under the curve that is associated with the test statistic. So if we plot the test statistic on the z-score curve, maybe I should write this down here. Let's see. With a mean of 0 and a standard deviation of 1, the test statistic is somewhere right about here. That's my test statistic, and I'll draw a line up to the top of the curve and shade the region in the tail here. Now, something to keep in mind, we are going to look for this area to find the p-value, but this is only going to be half of our p-value. And that's not always the case. Sometimes this shaded region will be your entire p-value, but for this example, it is half of the p-value, and that's because of our alternative hypothesis having a not equal sign, which makes this a two-tailed test. So if we were to have drawn in our critical values, we would have had 2 of them because our alpha would have been split up into 2 sides. And since our alpha is split up into 2 sides, we have to consider our p-value the same way. So whatever this area is, I'm going to double that to put the answer for the p-value. So how do we find an area under the normal curve with a z-score of 0.32? We can look up 0.32 in the negative z-score table as a z-score, so it'll be on the outside. So we're going to be looking up where it says 0.3 and the top where it says 0.02. So it'll be in this column, and that means I'm right at 0.375. So that little area has the value of 0.375. Kind of ran out of room here. So let's see if I can squeeze it in. Eval half is what was it again? 3745. Now I'm going to double that two times 0.3745. There's my 0.3745 times 2 gives me 0.749. Okay, finally, we have, I think, two more steps here. We're going to identify the conclusion about the hypothesis test. So that's determining whether we reject the null hypothesis or fail to reject the null hypothesis. And then we will talk about the conclusion as it relates to the claim. All right, so it says identify the conclusion for this hypothesis test. Well, we have a p-value 0.749, and we need to compare that to a significance level. The significance level was given in the problem as 0.1, so that's our alpha. So that's an area or a probability of making a type 1 error. That's the maximum probability of a type 1 error. And remember, a type 1 error is when we reject a true null hypothesis by mistake. So we're limiting that possibility to 10% chance. And if our p-value is smaller than that, it will be acceptable to reject the null hypothesis. So we want to compare our p-value. Remember that rhyme, if the p-value is low, the null must go. Low compared to what? Compared to the maximum probability of making a type 1 error. So we're looking to see if this is true. And if it is true, we will reject the null hypothesis. So the p-value was very high and definitely not smaller than the alpha. So we will fail to reject. Fail to reject the null hypothesis. That means we can rule out anything that says reject. So A is not possible and C is not possible. The only two answers that could be right are B and D. So we'll read the rest to see which one makes sense. The first one says there is not sufficient evidence to warrant rejection of the claim that the rate of inaccurate orders is equal to 10%. The second one, or D, the second option left, there is sufficient evidence to warrant rejection of the claim that the rate of inaccurate orders is equal to 10%. So in order to know which one of these is correct, there's a couple of ways of thinking. One of them is to consider whether your claim fell into the null hypothesis, because if it did, then you're actually failing to reject the claim since you failed to reject the null. So sometimes the null hypothesis and the claim are the same, or sometimes the null covers the claim, and you talk about the claim almost the same way you talk about the null. And other times the claim will fall under your alternative hypothesis, so that you will be discussing whether to support the claim. Another way is to use the flowchart provided in this formula packet. It's on the second side of the printed formula sheet for hypothesis tests, down towards the bottom. And notice that it'll lead you through the right questions and answers and conclusions to choose to word your final conclusion with one of these four things. So first we're asked, does the original claim contain the condition of equality? In this case, yes, because the claim was that the proportion was equal to 10%. So we'll go this way. Then we ask, do you reject the null hypothesis? No, we failed to reject the null. So then the correct beginning of our final conclusion is there is not sufficient evidence to warrant rejection of the claim that the proportion is 10%. So that was B. Because there's not sufficient evidence to warrant rejection of the claim, since we failed to reject the null hypothesis, and the null hypothesis was covering the claim. Does the accuracy rate appear to be acceptable? Let's see. That one's kind of a subjective question, but what do they mean by acceptable? Let me read the question again. In a study of the accuracy of fast food drive-through orders, one restaurant had 36 orders that were not accurate. Okay, so P hat represents the inaccurate orders and use a 10% significance level to test the claim that the rate of inaccurate orders is equal to 10%. Okay, so that means that the owner of the restaurant is claiming that the rate of inaccurate orders is only 10%. And we were unable to reject that claim. So since we failed to reject that claim, then I guess we'll say it appears to be acceptable. Okay, since there is, let's see, let's eliminate some options here. Since there is sufficient evidence to disprove the theory that the rate of inaccurate orders is equal to 10%. No, there was not significant, there was not sufficient evidence for that. So that's not going to be one of the choices. Okay, since there is sufficient evidence to disprove, no, that one doesn't seem right either. Since there is not sufficient evidence to disprove the theory, it is possible that the accuracy rate is acceptable. That seems right, so I'm going to go ahead and mark it, but we'll read the last one just in case. So it says, since there is not sufficient evidence to disprove, the theory that the rate of inaccurate orders is equal to 10%, the accuracy rate is not acceptable. The restaurant should work to lower that rate. Okay, yeah, so C is the best answer there. So let me go over and put in what I found here. For the p-value, we had 0.749. Identify the conclusion for this hypothesis test. We chose B, and then C for the next part. B, fail to reject. There is not sufficient evidence to warrant rejection of the claim. And C, since there is not sufficient evidence to disprove the theory, it is possible that the accuracy rate is acceptable. All right, so we did well. That was a great review. Thank you for that question. And if you guys don't have any questions, then I'll move on with the next section that we're covering today. I'll just go over to Blackboard while you guys are thinking about whether or not you have a question. It's not too late to ask if you do have a question. But I just wanted to show you on the syllabus, the course agenda for today. We were scheduled to cover 8.2 and 8.3. We've already done examples from 8.2. So we're working on, actually we've done questions from 8.2 and 8.3. So we're actually working on 9.3 today, which is claims about differences of means, basically hypothesis testing with paired data. So we're ahead, which is awesome. Gives you guys more time to process everything and get ready for the test. So as a review of what we've been doing over the last couple of classes, I might have a question, let me see. Is test 4 in the final exam? The final exam is cumulative, so you'll want to study all 4 of your midterm tests to prepare for that final exam. Okay. All right. I thought we could also, just for those of you who are interested, I just remembered that I can show you. Let me go back to my, What did I do with that question we were just working on? Is that it? There it is. Um, I can show you how to use the calculator, the TI-84. So you know that I've designed this course with the intention that you would not need to purchase this calculator and you would just be using Excel for most things. But I know some of you are using it and I have said that it's okay. So I'll show you, even though I don't normally include this in my lesson, we're ahead a little bit. So I'll go ahead and I'll just show you how you would do that same test we just did using your TI-83 or 84 family calculator. To do any kind of statistical tests, including hypothesis tests and confidence intervals, you'll go to the Stat key, and then you'll see it pops up to the Edit screen, and the Edit option is where you can enter data into lists. So if you have a problem where you're given actual list of sample values instead of the summary statistics, this is where you can enter those values. When you're ready to do the test, you'll go to Stat again, and notice that there's a couple more sub menus or sub options up at the top. One that says Calc, so that would be to calculate statistics, and tests. We're doing a test, and for this one, we would be doing the one proportion z-test. You can actually type the number 5 or scroll down using your arrow key and press enter. You'll put the claimed value up at the top where the subscript of 0 is, kind of like the null hypothesis. Then you'll put in your number of successes, your sample size. Now, if they don't give you the number of successes, but they give you a success rate instead, then you can multiply that success rate times n and calculate your x that way. Then you go down and choose the symbol for your alternate hypothesis, which for us was the not equal sign. And then you can either calculate or draw. So if we choose draw, it looks like this. And you can see how huge that shaded region is associated with this test statistic that we found using the formula, and how they show the p-value on both sides there. However, when you sketch this out for your test, there's a show your work section that you're going to fill out a form and upload it in Blackboard. I don't want to see the p-value colored in on both sides. The significance level, yes, but put just half of the p-value in the picture. You only get one test statistic, and for this it was a positive. So I would only want to see the one positive test statistic on the right, and then that shaded region on the right, and label it as p-value over 2 equals 0.3 whatever. Then there is a section of the form where you will enter the entire p-value. If we go back to that same menu and choose calculate, this is what it looks like. So you can see up at the top, there's your test statistic, the z-score of 0.32. The p stands for p-value, 0.746 when you round it to 3 significant digits. You can even see your p-hat. So the p-hat came to a decimal of 0.105. So that's pretty close to the claimed value of 10%, which is why we ended up failing to reject the null hypothesis. It's very, very close to the claimed proportion. All right, so let's go back to the beginning of this set of notes. This is from last week. We did a couple of student questions in the beginning. All this is recorded and accessible to you if you want to watch the sessions again. Then we did examples from chapter 8. We did this example. So this was example 1 for chapter 8 examples. And this was a claim about a mean. It was two-tailed. And we ended up failing to reject the null hypothesis. We filled out the form. We did the confidence interval as well. Then we did example 2, which was a claim about a proportion. And it ended up being a right-tailed test. And we filled out the form. and found that we would reject the null hypothesis and of the alternative. And so now we are doing hypothesis testing for a difference of means. Actually, I put that backwards. I need to fix that because it's the reverse of this. We will do a hypothesis test where we test two means against each other, but in this section, we will be doing the mean of differences. See how that's seems like it almost is saying the same thing, but it's not. We're saying the average of differences, plural, when we have paired data, also known as dependent samples. So when we're testing claims about matched pairs, there are a few things that we assume or we check assumptions for. In your circumstance, the questions that you're given will usually be already structured so that these things are satisfied. But we'll just review what those things are. First of all, of course, always we assume a simple random sample. 2, sample sizes are small, often small. And if they're small, then you know we might need to use the t-distribution. 3, 2 measurements or samples are drawn from the same pair of individuals or objects. That's what makes this paired data. And then we have differences calculated from the matched pairs. So we subtract the 2 values that were collected from each individual or object. 5, the differences form the sample that is used for the hypothesis test. And so what that means is that we take 2 lists of values, we subtract each set to get a difference, and then we have a collection of differences, and that's considered the sample that we're testing. 6, enter the matched pairs, either the matched pairs have differences that come from a population that is normal, or the number of differences is sufficiently large so that the distribution of the sample mean of differences is approximately normal. Number 6 refers back to the central limit theorem. Remember we said that the means would be normal if the original values were normal, or if we're not sure if they're normal or if we know they're not, then we can still use the central limit theorem when we have a sample size greater than 30. So I'll just make a note here about the central limit theorem. CLT says if X is normal, then the sampling distribution will also be normal for the sample means, or if N, not capital N, but sample N, lowercase, if N is greater than 30. All right, if a hypothesis test for matched or paired samples, subjects are matched in pairs and differences are calculated. The differences are the data. The population mean for the differences is sometimes referred to as mu sub d, just with a subscript of d on the mean, so that it reminds us what kind of test we are doing. It is then tested using a student's t-test, right? So in other words, t-scores instead of z-scores for a single population mean with n-1 degrees of freedom, where n is the number of differences. And this is the standardizing formula. And notice that it's still just like your z-score formula. Remember the z-score formula originally like this, or if we're dealing with sample means by the central limit theorem, x bar minus mu over the standard error, where we adjust the standard deviation, dividing it by the square root of n. And notice this is all really the exact same formula as this one, except it has a t, because we're going to use the t distribution, and we have little d subscripts to remind us that we're doing the differences of pairs. All right, so what does it look like in our little packet here? It's under dual populations, even though, in my opinion, the way it's organized, it's not really a dual population. It's a single population with two sets of values that we turn into a single set of values called the differences. But since we have two sets of information, we'll call it a dual population in general. And then it says for dependent paired, or for the mean of differences, we'll be using these formulas. Okay, and notice that those formulas are awfully similar to the ones we were using for the mean with sigma unknown. Okay, but it's, I mean, whether you used this one or this one, you'd get the right result. It's just the notation is a little different here. All right, so let's do an example. You wish to test the following claim, H sub A. H sub A, remember, is another way of saying H sub 1, two different ways of referring to the alternative hypothesis. At a significance level, alpha equals 0.05. For the context of this problem, mu sub D is the difference between two. That's actually incorrect. Ay, ay, ay. No, sir, that's not correct. In fact, that's a common mistake, to take each mean and then subtract the means. No, we don't want to do that. We want to first get the differences and then take the average of all the differences. Right, so let's ignore this line. Well, we don't have to ignore all of it. We can just take out the part that's incorrect. Let's see. What else does it say here? Where the first data set, okay, that's fine. The first data set represents a pre-test, and the second data set represents a post-test. You believe the population of difference scores is normally distributed, but you do not know the standard deviation. You obtain the following sample data. All right, so notice that they give us some sample values. And it's always convenient to be able to copy these, which you can do in your homework problems and therefore your test problems, since you're doing your tests online as well. And so you can either copy the table, and it looks different in your homework, but you'll be given some table of values. You can copy them and paste them into Excel, or remember there's an option to actually just open the data set into Excel. So we'll go ahead and copy and paste these into, I already have them here for us in Excel. And we're going to begin by taking our paired data, which this set right here is the pre-test score, and this post-test score of subject 1 in our sample. And then subject 2 has a pre-test score of 60.3 and a post-test score of 89.2. And this continues. You don't need the labels like this, but maybe it helps to understand what we're looking at here. So I want to know if subject 1, let's see, what was the claim again? Let's read that claim. That claim said, you believe the population of different scores is normally distributed, but you don't know the standard deviation, and you obtain the following sample data. Let's see, let's make a claim here. There's no claim written here, so let's make one. The claim is that the post-test scores are significantly higher than the pre-test scores. Okay, that would make sense because if you think about, if I gave you a pre-test before you had learned anything about a certain concept, and then after teaching you, I gave you a post-test, we should expect that the post-test scores are going to be much better. So if this is our claim, then we're interested in how much improvement there was from the first test to the second test. So using the example of the first set of data here, I'll use this as my example. Then I'm interested in whether subtracting the larger one minus the smaller one would give me a difference that is, hang on, we have to do it in order. I forgot. We have to do it in order, even though we usually subtract a larger number minus the smaller order. We always start with population 1 difference, or population 1 score minus population 2 score. And we want to see if when we subtract them, well, what would happen if I have a larger value being subtracted from a smaller value? What's the difference here? Let's just calculate it. First population, or first sample minus second sample. So I got a difference of -5, as I should if I'm subtracting a larger number away from a smaller value. And I wanted to illustrate that because that shows us that we end up with a negative. And the negative difference in general is what we would expect if our post-test scores are better or higher than our pre-test scores. So the claim is, in symbols, that the differences, let me write it out, claim differences are negative. Now, it's hard to test whether all the differences are negative. So what we'll do is we'll use a single value to help us with this. So what we'll say is that on average, the differences are negative. So to write that in symbols, we'll write the mean of the differences on average is negative, which would mean less than 0. Okay, so this is our claim in symbols. That would mean that our null hypothesis, which always uses the equal symbol, does not contain the claim, and therefore the claim is the alternative hypothesis. And that means this is a left-tailed test. Left-tailed test. Now, we can use the hypothesis testing guide to help guide us through the process, since there are a lot of things to think about. We can go ahead and write in mu sub d is less than 0. On average, the differences are negative. The null hypothesis, which always uses the equal sign. All right, so basically the null hypothesis simplifies to saying there is no significant difference between the pre-test and post-test scores. And the alternative, mu sub d, being less than 0, means that the claim falls under the alternative hypothesis. And the reason we like to be aware of this is because now that it's in the alternative hypothesis, our final conclusion will involve either there is or there is not. So we have to figure out which one of those. There is or there is not sufficient sample evidence to support the claim that post-test scores are higher on average. Okay, so I already know what my final conclusion is going to look like. I just have to determine whether I'm going to say there is sufficient evidence or is not sufficient evidence. And we also saw that there would be a left-tailed test, L for left. So I know that I'm going to have a critical value somewhere over here on the left, and my significance level alpha is also going to be fully contained on the one side instead of being split up onto two sides. Now let's choose a significance level. Usually it's given in the problem. I'm not sure if it was given here. Let's see. Oh yeah, it was. We were given this. So we'll go ahead and put that in for our alpha 0.05. We don't need to split this up into two tails, so we'll just ignore that second part of it. And now we'll find the critical value, which is a boundary. Is it a z boundary or a t boundary? It's a boundary for sure, but is it a z-score boundary? Well, we were given sample data. We were not given this. We were not given the population mean. We only know the sample. Oh, I just totally mixed up my words. Let me start over. Remember that if you are testing a claim about a mean, you will use z-scores if you know the true population standard deviation sigma. But if sigma is unknown, or in other words, if all you know is the sample standard deviation, then you will have to use the t distribution. Side note, if your n is large enough, you can still get away with using z-scores, but for your purposes, just use the t distribution whenever you don't have the sigma, the population. Okay, so we're using t because sigma is unknown. All right, so let's go and find the t-score boundary associated with an alpha of 0.05 or a left-tailed area of 0.05. A couple ways we can do this. We can go into our t-table and get something that's pretty good. Sometimes the t-table is difficult to use to get a good t-score. Usually, well, it's actually more difficult to find an area using this table. It's pretty good for finding boundaries. So finding a boundary, we'll need the degrees of freedom. What are the degrees of freedom? Well, that's always n minus 1. So we need to know how many sample values we have. Here's our sample data, but we don't count every single value because this really counts as just 6 subjects or 6 pairs. So our n is 6, which means we have 5 degrees of freedom. So we'll be in this row right here. And then we need to line it up with the correct column that represents the area in the tail of our sketch here. So our sketch has a single-tailed area of a total of 0.05. So in one tail, we have 0.05 area. So then the value that I want to use is 0.1015. So T is 0.015. Did I do that right? Let me see. I mean, I know I did it right, but it's 2.015. So I wrote it down wrong. 2.015. Also, we want to make a note of whether it's a positive critical value, a negative critical value, or both. So if it was two-tailed, we would select plus and minus. But here it's a left-tailed test, so we know that this is actually negative 2.015. Okay, now we've completed our red couple that represents the maximum probability of making a type 1 error. And now we can start working on the couple, the green couple, which is a boundary and an area representing our data. So let's begin with the test statistic, which is a boundary. So it should also be a t-score, just like the critical value is a t-score. We will find the test statistic in the t formula for standardizing our sample statistic. And remember what that was, this right here, d bar. Notice d bar instead of x bar, just because we want to realize that that's the mean of the differences, the sample mean, minus the claimed population mean according to the null hypothesis, assuming that the null hypothesis is true, divided by the sample standard deviation, and S, remember, means it's coming from our data, divided by the square root of n. So let's write that formula down, and then we'll use Excel to do the calculations. Sample difference, sample average of differences, minus population, I'll write that in blue, minus the claimed mean, then divided by the sample standard deviation of the differences divided by the square root of n. So we need to calculate d bar in order to fill in the rest of this, right? We can put in the claimed mean. So there's a few things we can put in here. All right, so the claimed mean is 0 from the null hypothesis. And the sample size, remember, was 6. 6 subjects, 6 pairs. And now I need to find from my sample data the mean of differences and the standard deviation of the differences. So we'll use Excel to do that. Let's first calculate all the differences. I can drag this formula down, or you can do them each by hand. Then we want the mean of differences. So I'll use the average function in Excel. And then the standard deviation of the differences, S for sample. And now we can use that to calculate our test statistic, the t-value. After we know the test statistic boundary, we can find the area that goes with it. All right, so let's write these values back into our formula. So the sample mean of differences, negative 19.35, goes there. And the standard deviation, we really shouldn't be rounding it, but I'll just make sure to put a lot of decimal places there. All right, so now calculating that here, again, I want to make sure my numerator is contained up here. So let's put some parentheses around the top. Don't forget about that negative there. And this is all being divided. Okay, so I'm going to put negative 19.35 minus 0. And you might be thinking, why would we subtract 0? Because it's not going to do anything. You don't have to, actually, but I'm just doing it. It's not going to make a difference. And then divided by the square root. Wait a second. Only the bottom has a square root in my divider, my denominator here. So let's put our denominator in its own set of parentheses as well. Divided by the square root of 6. Now, I've just closed my square root there. I need a second parenthesis after that to contain my denominator. Okay, so I'm getting negative 4.116 approximately for my t-score test statistic. All right, now for those of you who like doing the programming, of course, you were probably thinking when I was typing all those values in just now by hand, can't we just do it by making cell references? Yes, so let's do it with cell references this time. I'm still going to want to contain my numerator, but it's the sample statistic minus the claimed mean divided by the sample standard deviation divided by the square root of n. I have a little extra underscore that I hit by accident. Let me fix that. There we go. All right, now the p-value. Now remember I said that areas are a little trickier to get out of the table here, the t-table. So I'll show you how to get a good approximation of the p-value from the table, but we will be using the t-distribution in Excel to get a better answer. Okay, so with 5 degrees of freedom, I have a test statistic of what? Negative 4.116. Notice that these are all an absolute value, so we'll use the closest one is 0.4032, and that lines up with a single tail area of 0.005. So from this table, the best p-value I can come up with is 0.005 in a single tail. So let's go and put that as one option. Okay, but that's not very accurate. So let's see what we get when we use Excel. Using Excel, remember to get an area from the norm distribution, we used the norm dot distribution, and we also have a t dot distribution. And there's a few different options here. You can do a two-tail, you can do a right-tail. I'm just going to use the regular t distribution, which returns the left-tailed student t distribution. So that's convenient because we are doing left-tailed. And the x is our test statistic. The degrees of freedom is 5, and we'll choose yes or true, or just put in a number 1. Remember, 0 means false, 1 means true. And notice that this p-value is more accurate, and if you rounded it to 3 significant digits, that would be 0.00. Those don't count as significant. So the significant ones are 4, 6, and then use that little 6 at the end to round the 0 up to 1. So much more accurate, but the one you get out of the t-table probably work fine. I recommend using this instead, especially for your homework, which may require you to get a more accurate p-value. And we are uninterested in half of the p-value here because we're not doing a two-tailed test. Okay, so now we're ready. Now that we have completed our sketch, we have the red couple, we have the green couple, we just need to put them in the picture. So the test statistic is back here, negative 4.116. And the area to the left of that is the p-value of 0.00461. And I'm ready now to decide if I should reject the null hypothesis. Remember, in this step, do not discuss the claim, only the null hypothesis specifically. The decision about the null hypothesis when comparing boundaries. The boundaries are the t-score and the two t-scores, the critical value and the test statistic. So what we will say is that the test statistic is more extreme. I think I need to type because it's just too hard to write on here in that small space. Get some tiny letters here. All right, so when comparing boundaries, I know I'm going to have to go even smaller than that. The test statistic is more extreme. It's farther into the tail than the critical value. Therefore, we reject the null hypothesis. Or you can just say H sub 0. But make sure to say what you're rejecting. Don't just say therefore reject and leave it like that. Say reject the null hypothesis so that I know what you really, I know that you know what you mean. Now the decision about the null hypothesis when comparing areas. What are the areas? The areas are the significance, the maximum significance, or the maximum allowed probability of making a type 1 error, and then the probability of getting this test statistic if the null hypothesis is true. So what we're trying to see is it possible that this test statistic happened just as a fluke, or is this so extreme when considering the claim, is it so extreme that we should consider it's probably, the claim is probably incorrect? All right, so what we look at is if the p-value is low. Low compared to what? Low compared to the other area or the other probability. So the p-value is less than or equal, say less than, the significance alpha of 0.05. Therefore, we reject the null hypothesis. And that's the conclusion or the decision we should make both times if we've done everything right. Both when comparing boundaries and when comparing areas, they have to give you the same conclusion. So the conclusion about the claim, let's see, either there is or there is not sufficient sample evidence to support the claim that the post-test scores are higher on average. Remember to put a little note where your claim is. So I'm going to put a little C here next to the alternative hypothesis. That's how we know we're looking to support it if we can reject the null hypothesis. And in this case, because we've chosen to reject the null hypothesis, that means we can support the remaining alternative hypothesis, which contains the claim. So we will say there is sufficient evidence. There is sufficient evidence, so we'll just erase the rest. There is sufficient sample evidence to support the claim that the post-test scores are higher on average. Cool. Let's go on and do the hypothesis test. What I meant to say was let's go on and do the confidence interval at a significance level appropriate to match up with the hypothesis test we've just done. So our hypothesis test was single-tailed with an area of 0.05 over here, all contained in the one tail. And the critical value was a t-score. Oops, wrong thing. I wanted to look at the t-score was negative 2.015. Negative 2.015. Now remember that when we do a confidence interval, we will have to have two tails with the same critical value as in the hypothesis test and the same area on that same tail as in the hypothesis test. So this is going to be 0.05, but because it has to be two-tailed, it's going to represent only half of our alpha, and the other half has to be the same area on the right with a positive critical value, and that means that the total area in both tails is our significance level alpha of 0.10. So that makes this a 90% confidence interval. So when calculating the margin of error, remember it's always the critical value times the standard error. So that would be 2.015 times the standard error, which is your sample standard deviation divided by the square root of n. Remember, the standard error comes from our central limit theorem. So here's the standard deviation of differences, but the standard error, let's make another little space specifically for the standard error. This is different than the margin of error. This is the standard error by the central limit theorem, which is the sample standard deviation divided by the square root of n, which here was 6. So the standard error, 4.702, really shouldn't be rounding it, but we're going to, because otherwise we'd never be able to write anything down. 4.702 okay, so that makes our margin of error that's E. Now, let me double check to make sure. Yes, I used the positive critical value here. Remember, always use a positive because you are calculating E, which is a distance. Okay, 2.015 times the standard error, 4.70, whatever that was. And here's our margin of error. If we round that, since we're going to be using it to estimate a mean, and since means are rounded to one place more than the original data values. And since our data values are rounded to 2 places, I'm going to go ahead and round this to 3 places. That way, when I add it onto my sample mean, it'll work fine when I round my final answer. So 0.9474. Okay, so E 9474. All right, so then to estimate the mean of differences, it's going to be between the D bar plus or minus E. And then we'll see if 0 is contained there or not, or if the entire, remember the claim was that the differences on average should be negative. So if we see that both of our boundaries are negative, that will give us further support for the claim. And I have to stop there. We're out of time. I think I'll go ahead and finish it on here, even though you're, of course, free to go. But I'll have to, yeah, I'll leave it in the recorded session so that you can finish it up later if you want. And the next class we'll probably do a similar example. So let me know, guys, if you have any questions. If not, I'll see you on Thursday. Take care. Okay, so I'll be listening for any questions that pop up in the chat, but I'm going to go ahead and finish this for the recording. So I was just about to calculate the boundaries for the confidence interval using my sample statistic plus and minus the margin of error. So I know I'm adding and subtracting 9.474, and then my sample mean of differences, negative 19.35. So my lower boundary, LB for short, is the sample mean minus the margin of error. My upper boundary, UB for short, is my sample mean plus margin of error. So now I have the boundaries for my interval and my interval estimate, which estimates the population mean to be between 28.82, one place more than the original data values, and negative 9.8. Okay, so with I'm 90% confident that the true mean falls somewhere between these two values. So remember, the claim that we were testing was that on average, the differences would be less than 0 or negative. Notice that my entire confidence interval is less than 0, so that supports the claim. What's going on? With this? Oh, must have the wrong. Won't let me stretch it out the way I want. Maybe start over. this blue. That did not just happen. Hi. The struggle with technology. Oh, I see what's going on. If I'm inside the box, I can't resize it. So I'm just going to try to set this up one more time, nice and pretty. Right here. Size 10, blue. The confidence interval, so I'll write it out. The confidence interval estimate is entirely below 0. Another way of saying it is both boundaries are less than 0. Therefore, it could be true. I'll say the claim could be true. The claim could be true. Now let's also compare it to what we determined with the hypothesis test. Remember, the hypothesis test, we supported the claim also. So let's write that. The conclusion of the hypothesis test was to support the claim. So the confidence interval and the hypothesis test agree. All right, so that concludes today's lesson. I'll see you guys for the next class when we do a similar example and start talking about another type of test involving independent samples. And yeah, I'll see you then. Take care. Have a great day, Thomas. Okay, stop recording.